All right, and we're going to talk about thermokinetic relations for computing. My name is Jean-Charles Delvenne, and I come from University of Louvain in Belgium. I want to thank the organizers for inviting me and giving me the redoubtable honor to be the last speaker of the week. So I think that's, they expect me to keep people in until the end. Okay, so we're going to talk about, well, stochastic thermodynamics. I just came up on this Nature paper recently that tells the story a little bit of nanoscale thermodynamics, as they say, and very interesting piece of paper. And I read this at the end of the article, right? They say it's great, but so far it's not very useful, right? No major technological advances. And I mentioned, for instance, the uncertainty relations as a promising way. So my question is, okay, can we make any major advances in technological computing, technologies of computing? All right, so that's my question today. Don't expect too much though, all right. But the goal of this talk is in fact very similar in philosophy to David's talk just before, indeed. We're going to try to explain some of the trade-offs that exist in computing technologies, especially the current computing technologies, so the CMOS framework for computation. And this is going to be related to other talks of this week. I named here a few names, a few ones. And for this, we will need new theoretical tools, which are called the Thermo-Kinetic Relations. All right. So I will not go too much time on this because David has explained it very well. But the basic circuit in today's computers is like the inverter or the NOT gate, right? You start with a 0, you end up with a 1, or conversely. A 0 means 0 volt, and a 1 means a certain level of voltage, for instance, 0.2 volts. Okay. And what does it look like? So this is a more simplified scheme that David and Nigel previously in the week has shown. So basically, the output of an inverter is a voltage, and this is the voltage at some plate of capacitances that are inside the inverter, right? And just to be very schematic, the rest of the inverter are nonlinear resistances, in fact, transistors, right, which can be seen as resistances, which are nonlinear and influenced by the input voltage, right, tuned by the input voltage. And so a 0 or a 1 just differs in the voltage at the output, so in the charge within those capacitances. All right, so how many electrons are up here in the pink zone determines whether we have a 0 or a 1. Okay, so with that, just as David showed, we can do memories. So this, if you put 2 in a row, well, then you've got like 2 stable states. So you got 1 memory, a 1-bit memory, all right? Too far. Okay, this is a clock. If you put 3 of them in a row, then there is no stable state. A 0 creates a 1, creates a 0, creates a 1. So there's a contradiction. So the 0 here becomes a 1, then 0, etc. Right? So we've got a limit cycle, and that's a clock. That's how a computer measures the time. So with just inverter, you can do a lot of cool stuff, right? So if you understand the inverter, you already understand a lot about computing. Now, if we want to do this trade-off, understand the trade-off of the inverter in terms of energy, in terms of speed, in terms of reliability, well, you have to choose a model for the inverter. And if you say, for instance, well, the inverter is just a general physical system, what comes from that? Well, then nothing. You've got no trade-off because the land hours cost for an inverter is 0. You've got no erasure of anything, okay? So Landover is very cool because it always applies, but here it's completely useless, unfortunately. The other end of the scale is to say, okay, I'm going to do a very detailed model, just going back to the physics or using experiments to calibrate my model, etc. So I've got a model that works for a single device, but it will be correct. This is the ground truth, right? We want to go in between, see which assumptions are sufficient to get an idea of the trade-off that the inverter satisfies without assuming too much either. So keeping some genericity, yet some powerful bounds that explain what's going on, right? So we can go at different levels of generality. For instance, you can have a Markov chain model that is specific to the transistors. And Nahuel has presented such a model earlier in the week, and Massimiliano as well. And you can have the model in that paper of last year. We want to be a bit more abstract in this talk. For instance, we can say, okay, I don't know much about my inverter, but it's overdamped for sure. Okay, and let's say it's an overdamped Markovian system. What can I say from that? For instance, can I use the speed limits, etc.? And that's where we can compare it to David's talk. Or we can have other assumptions that the inverter satisfy in order to get those trade-offs right. All right, so that's where we introduce the first thermokinetic relation in this talk. That's an upcoming paper, and you've got the link in the chat if you want to see the detail. So what is this? Well, I suppose that I have a time-varying Markov chain, all right? And then now I put an anti-symmetric observable, just like in the thermodynamic uncertainty relations, right? So here we've got, like, let's say, two transitions, and then I put a weight, so a number, on each edge so that you've got the opposite sign on the opposite edge, right? And so the result is this. We've got like a frame here. It involves both the average of f integrated along a trajectory, along arbitrary time intervals, and the integrated absolute value of f, right? Here I've got the inverse hyperbolic tangent function, which behaves like this. So in particular, it's larger than identity. So if you want like a simplified bound that looks simpler, you've got this, okay? Okay, that's good. What can we say about this? So the entropy production is bounded by something about the mean value of the observable and the mean value of the absolute value of the observable, right? So that's what I call a thermokinetic relation, because it says, okay, thermodynamics is constrained by the kinetics, by the statistics of specific observables, all right? So what can we say about that? Well, you might think it looks like a bit a thermodynamic uncertainty relation, and indeed, it makes sense. So the relation makes sense, gives a non-trivial result already for stationary processes, right? So if I compare to the standard thermodynamic uncertainty relation, I can play with, let's say, a little model, so-called kinesin, which is a molecular motor, and practically speaking, I mean, mathematically speaking, it's a stationary Markov process, right? And so I can compute everything there. And here I've got like the entropy prediction, so the actual entropy prediction. Here, the bound predicted by the bound I've just shown just before, so the thermokinetic relation. And here, the classical and the usual TUR, all right? So sometimes better, sometimes worse. That's normal because we use different quantities. We don't use the variance, we use the absolute value of the fluctuation. So of course that's different, okay? But this is not really our concern today. We are more interested in the speed limit interpretation of the thermokinetic relation. That's where we are being non-stationary. And we can prove from the relation I showed you that if we now put a symmetric cost on the transitions, symmetric number, right? So here you've got the same on E, and on E bar, the reverse transition, and we interpret it as a cost, as a difficulty, let's say, to make a transition. If I put 1 on every cost, then this is just the activity. We just count the number of jumps. But I can put other numbers that could be application dependent, right? And then what I get is like a speed limit that involves the Kantorovich or Wasserstein distance between the initial and final distribution on the states, and, well, the activity, so total number of jumps, or something else, right? The integrated weight over all the transitions of the path. Okay, so this is a generalization of a result by Andreas Deschamps last year, and but the new thing here is that instead of the activity, you could have anything that is your observable of interest. And we will see an example just now, in fact. Okay, I apply this to an electronic device. So it could be the inverter, or it could be the memory, like the 1-bit memory, or it could be the clock or whatever. But I just measure a bit, right, at the end of this. And so what is going to be my observable of interest? Well, I count it as the influx of charge into the pink part, right? So into the place where my bit is decided is a 0 or 1, depending on the voltage. So depending on the number of electrons, right? So if an electron, QE, is coming, then my observable during this transition is plus QE. If it's leaving, minus QE, right? So I just keep track of how many electrons enter or leave my capacitance. And if it's a transition that does nothing to my out capacitance, I do nothing, right? In the black box, plenty of stuff is happening, but I don't count it, right? So if I take the absolute value of F, well, it's like an activity, but an activity just for the observable part of the system, right? The output part of the system. So it is not the activity of the full system. And that's good, because the activity comes in the denominator, right, in your in our speed limit. So we want a small one, okay? So we hope that this is going to be a better bound than as if we counted the full activity for all the electrons jumping left and right in the black box, right? So with that in mind, we're going to compute the prediction on the entropy prediction on the switch from 0 to 1, or from 1 to 0, all right? So what do we get? So what do we get? All right, here is the adaptation. So if I take our thermokinetic relation, here is what it gives, right? The integral of the charge, well, it's just the difference of charge between a 0 and a 1, right? So the difference of voltage in a way, right? Proportional to the difference of voltage between a 0 and a 1. So that's very clear, very easy to measure. And here, the total number of times that an electron enters or leaves the capacitance, right? And this is our formula. And so it's pretty generic, because it doesn't depend on what happens in the black box, right? It just depends on the way we encode the output bit of the circuit. So let's see what it gives on an actual example. Okay, so we take an ultra low power inverter, so like with small voltages, 0.2 volt, between a 0 and a 1. And that's the kind of thing you can actually find in Internet of Things. So basically connected watches, for instance, right, where they need very low power. And what the numbers I give here, you shouldn't take them too seriously. They are like sometimes back of the envelope calculations, but based on realistic simulations. So on the ground level, realistic modeling of an actual transistor, right? And here is the numbers. So basically between a 0 and a 1 in those transistors, you get like 300 electrons, plus or minus, right? And the total number of back and forth of the electrons is like in the 2000s, okay? So if I put the numbers together, right, in the bound, I get something like this, so 100 kT. So this is a prediction that given what we know about the process, we need to spend at least 100 kT to switch the bit, okay? And in reality, we've got something more like more than 1,000, right? So 17 times more. So at least we've got like an order of magnitude that is not ridiculously different, right? Up to a factor of 20, let's say, we can predict the entropy production generated by between a 0 and a 1. All right, so that's good. That's the first step, but it's not great either. So let's see if we can go a bit better, right? So far, we didn't account for the reliability. So sometimes you encode a 0, but if you try to read it, you will read a 1. Okay, why? Because you've got the average charge, Q0 or Q1, that encodes the 0 or the 1, but you've got, of course, a variance around that, a variability. And if I take the probability distribution corresponding to a 0, or a probability corresponding to 1, well, they overlap, unfortunately, and that's why you can make mistakes, right? If I have a 0 in my system, but at the moment where I measure the state of the system, the charge, I see I am in the yellow part here, I will conclude that, in fact, it is a 1, so I will make a mistake, right? So this is a simple model for the error that can be made in a CMOS circuit. We have to measure this epsilon, the size of the tail that overlaps the other distribution, right? And in fact, this is related to the total variation distance between the two probability distribution. All right? So this is how I measure the unreliability or reliability of my circuits. If there is a lot of overlap, then there is a lot of noise, right? And this is where the initial reader comes, right? If you got a car and you want to go from A to B, what's the best way? Well, you push the gas as much as possible, meaning you accelerate as much as you can. And at some point, you brake as much as you can, right? You push on the brake. And you have to compute exactly when you have to switch from one to the other, okay? Remember that you have to be at 0 speed at your destination, right? So you have to brake at some point. And that's optimal. So the optimal is to go bang, bang, right? So bang, you accelerate as much as possible. Bang, you brake as much as possible. This is also called an on-off control. And it's pretty generic in optimal control theory to have that whenever your input force is bounded on both sides, right? So you try to keep to the bound, and you have to know just when to switch from one to the other. Here I refer to Stephen Blaber's talk, who talked about similar strategies, right? So here we just take the pure bang-bang strategy. And a bit switch is exactly like that too, right? It's easy to implement and it's fast. And indeed, when the input jumps from 0 to V in, it jumps it very fast. And so the output now decreases quite fast as well, but it decreases when the V in has already reached a high level, right? Because there's a little bit of delay. And we checked empirically, so on our model, that indeed those curves represent, I mean, this is a cartoon, but in reality, it's pretty much like that. So we really have a bang bang, so a very steep ramp at the beginning that can be approximated by a pure step, okay? So we've got a bang bang control. That's another assumption we bring to the picture, right? It's not only an overdamped system, it's an overdamped system following a bang-bang behavior, bang-bang control. And so for that, we've got also a thermokinetic relation relating the entropy production to the reliability, knowing that we are in bang-bang, meaning we go as fast as possible in this regime, right? So this is in a paper that also appeared in the Journal of Physics A. And let's do it, right? Again, we've got numbers that are a bit of back of the envelope calculations, but still plausible. And we've got this probability of error, so very low, right? And if I put the numbers together, I've got something like 300 KT. So that's better. Now I'm only by factor 5, let's say, something like that, right?
A couple more minutes.
Thank you. All right. So as a conclusion, what did we do? We've got new thermokinetic relations, so bounding the entropy production by kinetic variables. And thanks to that, and thanks to the apparatus of stochastic thermodynamics, we can recover the trade-offs of current CMOS technology, not perfectly, but just up to an order of magnitude, right? And without having a detailed modeling. So I think that this kind of thinking, not just of this talk, of course, but all the interesting things that have been said during the week, maybe can help analyze and design CMOS technologies or even non-CMOS technologies in order to try which kind of strategy, bang, bang or not, for instance, can put some affordable trade-offs, let's say, given also the constraints that future technologies must follow. So for instance, the energy consumption, as David underlined. So I think I still have a slide normally. All right. Yep. Okay, and that's for all for it. I just wanted to underline how I enjoyed myself during this week and thank my co-author, Massimiliano Esposito, Gian Maria Falasco, Nahuel Freitas, and Leopold van Brandt. And also I wanted to advertise that we have a postdoc position. This is a joint project with Esposito Lab in Luxembourg, but this is a postdoc for in my group at University of Louvain and on the cost of computation. So basically this. All right. Thank you very much. I'm happy to take questions, either now or just write to me, send me an email, and I'm very, very happy to talk with all of you and discuss, collaborate, etc.
Thanks very much.